Yeah. Yeah, so this is kind of the backdrop for the tactic for Cubical Agda that I'm trying to implement here during this workshop. So this is more a theory talk, I guess. Yeah, so everybody who has used Cubical Agda has seen that we have a new kind of proof goal that we need to solve there. If we work with higher inductive types and we, for instance, eliminate into or out of a higher inductive type, then there's a proof goal path P of something complicated, or if you then refine it, you have introduced some interval variables and then you get some boundary conditions, and then you need to give some term which satisfies these boundary conditions. So this is all quite intricate to do for newcomers, but also if you're used to it still, it is quite difficult, I think. So the idea would be to automate this and maybe make Cubical Agda a bit more beginner-friendly. So this is kind of the immediate takeaway from this project. More broadly, I hope, I mean, cubical type theory, I guess, is kind of the first approach to getting computing univalent type theory. It might not be the last one, but I think this way of reasoning with cubes is actually something quite interesting that might be independent of cubical type theory, actually. So there's this paper from 2015, which just works in plain book-hot and uses cubes to structure the reasoning, which is quite interesting. So kind of looking at these cubical goals and seeing how we can solve them systematically, I think, is an interesting endeavor independently of cubical type theory. And more broadly, I mean, there are univalent type theories. There are also other approaches to higher dimensional logics, which kind of allow us to talk about higher dimensional categories or spaces in some way. So there are some globular approaches, which I think are not as well known kind of among type theorists, but which are also quite interesting, and maybe looking at cubical type theory, but at some point also at these other approaches, also maybe simplicial type theories, and understanding a bit the complexity of proof search in these higher dimensional logics for proof relevant equality can be useful to get a different angle on this issue of getting proof relevant equality work well in a logic. So this as context. So we've just in this talk talked about by Antoine talked about connectives. And what the idea of cubical type theory is, if we have some higher inductive type which describes a cubical set, so we have some cells lying around in this cubical set, then we use abstraction application to transform some of the cells into other cells. So the generators or the constructors of the higher inductive type give us some primitive cells, and then when we introduce some interval variables, we construct higher dimensional shapes because we can use these interval variables, and then if we apply some formula built from the interval variables in the context to some cell, which is a constructor of the higher inductive type, we kind of shift the shape of this constructor. So in this way, these two kind of constructs imported from how we talk about functions allow us to contort a cell in a cubical set. So this is a quite nice syntactic way to talk about these contortions. I'm going to call them in the following, but they're not very apt for automatic proof search because it's quite difficult to see how the boundary of a contorted cell comes about when you just look at these formulas, which is why we need a different characterization of these ways of transforming a cell into a kind of cell of a different dimension or different shape. And this is the correspondence between these n-tuples of elements in a bounded distributive lattice. So we are not talking about De Morgan cubical type theory here, just about Dedekind cubical type theory. So we don't have reversals for now. So an n-tuple of terms in M of terms in a lattice with m elements corresponds to having m abstractions over interval variables and then applying n formulas to a term that you have given as a construct of the higher inductive type. So in this way, this is kind of how we talk about a cell in Cubical Agda. And now there's a bijective correspondence between these tuples of terms in this lattice and poset maps. So if you just consider the two-element poset and take the nth power and the nth power, the monotone maps between these two posets correspond precisely to these tuples of terms in the lattice. And this correspondence is what we'll use to come up systematically systematically with cells in a cubical set. So let's make this more precise. Cubical sets are usually defined as pre-sheaves over some base category. So the base category we'll consider is the Dedekind cube category with this formulation. So you could have well used the lattice formulation, but we'll use this poset map formulation. So our base category is the full subcategory of posets, where we'll only consider the posets which are powers of this two-element poset. So then an element in 1n is just an n tuple of indices 0 or 1. And then, since we take the full subcategory, this means we'll also only have morphisms which are monotone maps between 1 to the n to 1 to the n. So some very important such morphisms are the degeneracy morphisms, which send 1 to the n to 1 to the n minus 1, which just forgets the ith index. So this is an element of 1 to the n, right? We have n indices, which are either 0 or 1, and then we'll forget about the ith one. Conversely, the phase morphisms will insert in 1 to the n minus 1 an element at the ith index, namely e. So this way we construct a morphism from 1 to the n minus 1 to 1 to the n. So these are not all the morphisms. We can't factorize our category with only these morphisms, but these are quite important ones. And now cubical sets are just objects of, are just pre-sheaves over this base category. So we'll see an example soon. But this means then, since it's a contravariant operation, when we then take the what Si is mapped to in a cubical set X, this will then actually increase the dimension of the cell that we are considering. So if we have here for sigma S, Si, for instance, then XSI will be a function from the n cells to the n plus 1 cells, which means we'll kind of consider the degeneracy of some cell that we have been given in our context. And in general, if we have a poset map sigma, we'll just use this notation in the following, where this means we'll consider what our cubical set does to this map, and then apply this to P. And the intuition, the geometric intuition is if P is an n-dimensional cell, then taking the contortion with respect to this poset map will make this n-dimensional cell into a m-dimensional cell. So we change the dimension of the cell. We can decrease it or increase it. And in this way, it's an m contortion. So that's the terminology that we'll use. For instance, if we take the face maps and contort a cell P at these face maps, then the collection of all these face maps will be just the boundary. So if we have a square given, then the contortions of all the face maps will just give us all the side paths of the square. So I've thrown a lot of definitions at you. Let's make sense of them with some examples. So a high inductive type in our setting, we'll not care about dependent type theory for now, just about cubes. So the dependent high inductive types is then given by giving a list of constructors and their boundaries, and then we'll say that all the contortions that we can build from these constructors we'll assume are in the cubical set. So this is what the type theory would ensure, that we can transform all these generating cells into other cells with the operations that our cubical index category gives us. So for instance, here we have an interval, high inductive type, which has 3 constructors, 0, 1, and a segment. So 0 has an empty boundary, which means it's just a point. 1 has an empty boundary, which means it's just a point as well. And then the segment is a 1 path, because it has 2 boundary cells, namely 0 and 1. And we can kind of depict this as seg is just a path from 0 to 1. Now, what we'll call the second loop space, because that's kind of what it stands from in the cubical library, has 2 constructors, so A and a 2-dimensional path P. So A is just the base point again, and then the P is a square, because we have 4 boundary paths given, and each of these paths is a contortion of the base cell, because the base cell is 0-dimensional. A square needs 1-dimensional boundaries. We'll make this A into a 1-dimensional cell with S to the 1. So we can depict this. P is a square filler, where at the boundary we always have a constant A path, so this means the vertices will also be just A. Yeah, and in this way we talk about cubical sets. So it's just a subset of higher inductive types in Cubical Agda. We have a third example, which we might have some time to talk about later on, but this just as a setup. Does this syntax make sense?
Yeah. Good question. So this P has 4 loops at its boundary?
Oh, it's not a loop. These are not loops really. These are just the boundary cells really.
Oh, they all 1 point. So this is basically a sphere then.
Yeah.
Okay.
Yeah, might be a better name actually. Yeah. Yeah, good point. Yeah, so we've done a lot of work of talking to talk about the things we could already talk about. What's the use of this? Or just one example. So if we take this interval high inductive type, like this is a term you would see in Cubical Agda, because yeah, we have 2 interval variables that we abstract over. So we have 2 names in our context, which means we talk about a square. And then we apply some formula built from these interval variables, I or j, to this path. So since seg is a 1-dimensional path, we can apply exactly 1 argument to it. So this way we talk about cells in Cubical Agda. Now in our setting, this formula corresponds by some transformation, which is not immediately obvious, but it's like a one-to-one correspondence that you can compute quickly, corresponds to this poset map. So we have 2 interval variables, and in this way we go from 1 to the 2 to 1 to the 1. And the map sends 0, 0 to 0, and all other elements of 1 to the 2 to 1. So this is the contortion of the seg path, which corresponds to this term in Cubical Agda. And the nice thing about this characterization of this contorted cell is that it has a very direct geometric intuition. So this poset map up here we can depict like this. So this is our 1 to the 2 poset, which sends all elements monotonously to the 1 to the 1 poset. And now, since there's the cubical set is a presheaf, this map will be turned into a map from the 1-dimensional cells to the 2-dimensional cells. And in this way, if we draw in kind of the definition of the seg path, this 1-dimensional cell gets mapped into this square by following along the mapping of this poset map. So this directly then makes it apparent that OR connective will create a square which has the seg path here and constant 1 paths here and here, because this 1-dimensional cell, for instance, if we follow along these 2 lines, we'll both have a 1 here, so this is really a constant 1 path. So in this way, this alternative characterization has really a geometric intuition that we can leverage when coming up with such sets, because that's the proof goal or the computational problem that we have at hand. We are given some higher inductive type. So now we'll look at the sphere, and we're given some boundary. So this is a 3-dimensional cube because we're given 6 squares, which we then want to fill. And in order to fill this boundary, we'll have to come up with a poset map, which will, if we apply it to P, give us a cell with this boundary. So this is essentially what the problem you're faced with when you're working in Cubical Agda. So just as a reminder as to what this boundary here would look like as a proof goal in Cubical Agda. So in Cubical Agda, you might be faced with a hole which has this type. So a triple nested path P type, which at the innermost level has this Pi and J, or and the second formula which is applied I or J. And so this is a 2-tuple of formulas in 2 variables, which corresponds to this poset map here from 1 to the 2 to 1 to the 2. So this is what we want to solve for now. We want to come up with a sigma that contorts the given cell to a cell with this boundary. And now, before we kind of do this, we already realized that in this instance, we already have a lot of options available. So in general, if we look at the morphisms from 1 to the 3 to 1 to the 2, so this is the kind of poset map that we want to construct because we turn the square into a cube. Then we'll have the third delegate number to the number of, we have I to the 3, 1 to the 3 to 2 to 1 to the 2, which corresponds precisely to the third delegate number squared poset maps. This is what gives the delegate cube category its name. That the number of morphisms in this category is precisely the delegate numbers. And these delegate numbers grow extremely fast. So the third delegate number is 20, the fifth one is over 7,000, the sixth number is over 7 million, and we haven't even computed the ninth delegate number. So we can't even enumerate the number of poset maps we have there. So before we start out coming up with such a poset map, we want to have a nice data structure which captures all these poset maps, and then in the next step we'll also explore this search space a bit more efficiently than just brute forcing our way through the search space. So last definition, I promise. We'll capture a collection of poset maps with this notion of a potential poset map. So instead of going from 1 to the m to 1 to the n, we'll now go from 1 to the m to the power set of 1 to the n, which means we'll collect all the possible values that that a poset map could give to something in the codomain, in the domain. And we'll have some conditions on these valuations at each point that ensure that we don't have any superfluous values. So this can be already used to, if we know something about the boundary of a goal, to narrow down the search space significantly. So this is what we'll see in a bit. So for instance, if we look at our interval high inductive type, which had these two constructors 0 and 1 and the one path sec, then a potential poset map, for instance, could send 0, 0 to 0, 1, 1 to 1, and for 0, 1 and 1, 0 we haven't decided yet. So in this way we can depict this as, okay, this guy will be sent to 1, the topmost element will be sent to 0, and for the middle elements we don't know yet. And in this way, this potential poset map captures 4 poset maps, so we can choose these 2 values independently. So we have these 4 squares represented by this one potential poset map. And what's helpful, so we see these just differ in the values we give to the middle elements here. So we've represented 4 elements of our search space with this data structure. But even though we look at a family of poset maps, we can still infer some information about all of these poset maps. So for instance, all these 4 squares have in common that we have a 0 here in the bottom left corner and a 1 in the upper right corner. So this will hold for all these squares, no matter where we put the other elements in. So in this way we have a quite concise representation of the whole search space, while at the same time still being able to narrow down the search space, which we'll now see with the example that we saw 3 slides ago. So recall again, we look at this 2-dimensional sphere. So we have A as a point and then a P, which just builds a sphere around this point. And now we want to construct something with this boundary. So as said, we are looking for a poset map from 1 to the 3 to 1 to the 2. So this is 1 to the 3, which already looks a lot like a cube, right? So this is just the Hasse diagram of the poset, but we can already see this will, in the end, be a cube. And here, this is 1 to the 2, where we've already filled in the definition of P. So P has A vertices in all 1 cells, and these are constant A paths. And our goal is to map this guy into the cube in a continuous way in some way, which is what the homogeneity condition of the poset ensures, such that our constructed cell has this boundary here, above here. And now to do this, we'll just go through the boundary and see what this boundary tells us about the poset map. So we start at the left. We see that, okay, this guy here, this is the face of this cube, kind of at the side where all the rightmost indices are 0. So just by looking at the boundary that we want to construct, we know that we have to send this face of our cube to these elements precisely. So we just look at what our poset map of P, or what our poset map controls P to, is at this face, and this nails down what the poset map needs to do on these 4 elements. So there we've already gotten a lot of information as to what our contorted cell must be. And then, just by the monotonicity conditions, we can also infer some more information. So this potential poset, yeah.
Sorry, maybe a stupid question, but why do you have 5 A's there when you have 6 cube faces? Is it? Am I missing something?
So this is the 6th phase.
Oh, right, okay, because it was the defined partial.
Yeah.
Right, sorry.
So we look for a contortion of P, and one of the phases is itself a contortion.
Right. Okay.
I think that's what's confusing. But this is a 2-dimensional cell, so this is really a square here.
Okay.
The question is, how do you know which one it is? I mean, if there are 6 of them, are they ordered in?
Yeah, it's just by convention. Yeah, it's the convention you kind of use.
And what is the convention?
So the convention I've used is that the first one is where the rightmost index is 0. So all these 4 elements here, we go back to this one, have a 0 here. So this is kind of the first phase of our cube. And then the next phase would be the opposite square. So this guy here where the rightmost index is 1. And then the next one is where the second is 0, and thereby we kind of go through all the phases of our cube in order.
And there is no sort of syntax indicating that convention? I can imagine, I mean, you're trying to make something simpler here. But if you have a list of, say, 48 elements, and like, whoa, okay.
Yeah, well, I mean, for the cube solver, it's simple. But like this is what essentially like the boundary of a cell has the first phase has the one index is 0. So if we kind of trace back this phase map to this guy, this means we'll forget about the first index we see. This probably starts from the left. So I might be actually not completely consistent with my notation here. But I mean, this is just how you set up the framework, I guess.
The reason I'm asking because on the previous slide, when you have these 4 examples, they were in another order.
These were...
The last one seems to be the first. The last one has on the right 3 zeros and a 1, which would seem to be what? Seem to be a natural order to those 4, which would be the last one first.
Yeah, perhaps. Yeah.
But then make that.
Yeah.
See something.
Yeah. Yeah. Perhaps. Yeah. For now, we'll just stick to this convention. But in the presentation, also, it might make sense to be a bit more explicit here. But coming back to our considerations, we've observed that this face here needs to have this assignment to our generating cell that we want to contort into this cube. And then, since we know that this guy here is sent to the bottom element, and what we construct is a monotonous map, this means that this guy also will need to be sent to the bottom element, because otherwise monotonicity will be broken. So this way we also know that 1, 1, 1 has a certain value. And something similar applies to these 2 elements, which we haven't even looked at the other faces yet of our proof goal. But because these 2 cells are sent to this guy, this means that these 2 cells, which lie under one of these, have to be sent either here or here, also again to respect monotonicity. So this means just by looking at the first phase, we've narrowed down our search space significantly, because all the grayed out vertices of our cube are already sent to a fixed value, and only for these 2 guys we have a choice between this one and this one, and for this guy we don't know anything because it only lies below the bottom, the top element, which was sent to the top element here. So 0, 0, 1 could be sent to either one of these vertices. So starting with our 400 possible poset maps, this is a potential poset map which would unfold to 10 actual poset maps that we could check manually if they give us the required boundary. So we've narrowed down our search space. And this is essentially what we'll do in our algorithm. So in here the pseudocode, I'm not sure it's too intelligible. I think this crowd I could probably better show the Haskell code. But yeah, so this is this cube solver. So we start with some generating cell in our context and with the proof goal, and we want to come up with a poset map which has a boundary given by the goal t. And we find such a contortion by first creating the total potential poset map. So this will be the complete search space here, which we can represent as a data structure concisely. And then we'll go through all the faces of our cube, and then we'll record all the possible values that each of the elements in this face could be sent to. So we'll go through all the values that our potential poset map at this point could create, and if this matches our goal boundary, then we'll add this to our potential poset map and update monotonicity of the potential poset map down here. So this is essentially what I've shown you with this example. So the algorithm implements these considerations. And what I haven't shown you yet is, so we've only looked at the first phase. Like if we go through the other phases, they seem quite trivial, just the constant a square at all the other sides. But in fact, they'll also nail down the potential poset map up until we only have a single value in our potential poset map. And this is due to the fact that we can't send, for instance, all these 3 vertices down here to the bottom element, because this would mean that the boundary here on this edge from 0, 0, 0 to 0, 0, 1 would be a diagonal of this whole square, which is in the constant 1 path. So this way, actually, this boils down to a single value in our potential poset map that we would find after applying this algorithm.
So I'm a bit pessimistic. We will go through all of your slides because we are trying
Yeah,
to
yeah,
half, and the talk
Yeah.
time is now.
Yeah, I think then 2 more slides, which are important.
Okay.
So, I mean, here we've narrowed down our search space from 400 to 10 poset maps. When we go in higher dimensions, this gets really relevant because if we consider a 5 cube, which is an kind of analog of what we've just seen, our approach just computes in a few seconds. So we'll have to try out all the poset maps for all the faces. So we have 10 faces, and each of these faces could be one of these 28,224 possible face maps. So this roughly means we have something in like hundreds of thousands to check. We can actually be more clever than this algorithm. I haven't really nailed this down yet, but like this is, I think, also improvable. Whereas when we would have to brute force our way out of this, we would have over 57 million poset maps to check. So this is not really feasible anymore with the tactic. Here you would run a runtime of over an hour to check all these manually. So I think kind of this approach can be improved because here we can probably be more clever than just computing the poset maps of all the faces explicitly. Yeah, this is work in progress, but even with this approach already we kind of get to higher dimensional cubes way more efficiently than with the naive approach. So just as a hint, this also works for Khan cubical sets. So these these contortions are of course not all the cells that we build in cubical type theory. When we build an H-comp, this means that we actually look for an open cube with a certain boundary, and then we use the filler that Cubical Agda provides to fill other goal. So this approach can be extended to Khan cubical sets, but I think this kind of simple case of just coming up with formulas for a cell is interesting. Even though there's a finite search space, it grows so rapidly that putting some energy into trying to search this more efficiently is interesting, I think. Yeah, so for Khan compositions, you can kind of extend our approach to also come up with open cubes. Yeah, and maybe what's what I learned here is that I'm now, so this is implemented in Haskell, and I'm now trying to make this usable from Agda. So I've already discussed this with a few of you, but maybe there's some other people who have some recommendation as to how to implement this best. So the current idea would be to use reflection to extract the proof goal and construct the context, then pass this to the Haskell solver with exec2c, then the Haskell solver does its work, gives some string, which is just an Agda term back. Now the current challenge is to have a reflection primitive which passes this string into the internal syntax of Agda. So I hope this will be available soon. Maybe that's not here, right? Yeah, and then this would be usable for in Cubical Agda. So hopefully there's some progress on this in the next 2 days. Yeah, and then there are some other ways to extend this proof solver, but I hope not the main idea. Yeah, I'll go across. Okay. Any questions?
So I have 2 questions. First, why didn't you implement it in Agda directly?
Have you seen the algorithm?
No, but I mean,
Yeah, so for now, I think, yeah, I mean,
is it so difficult that you would actually have, like, do you need external libraries, for example?
no, the Agda
Does
is
that mean-
total, so that makes it kind of more
You can
difficult
always
to explore
use fuel,
algorithms.
right?
Yeah,
You can use fuel, or you can just start out with allowing non-termination.
yeah, it's true. I could have done that, but still, I think at some point it will be still good to have it as a Haskell code because you can optimize Haskell code more easily than Agda code. And like performance is actually relevant in this setting.
Also, I think, I mean, you have an upper bound, right, on your computation steps. At least as long as you know the delegate numbers.
That's true, yeah. I could just give fuel.
So yeah, for low dimensions, you actually know exactly an upper bound of the fuel.
Yeah.
So then my what was my second? Right. Do you care about like uniqueness in this setting, or do you just care about putting anything there?
Yeah, just about putting anything there. So we could also give multiple solutions to a user, but I think for now, one solution is just fine.
Okay, so it's really more about yeah, you have a function that you want to define. It's like, well, as long as you can glue something in there, I'm happy.
Yeah, and because you can use elaborate and give, you can even give back the term to the user, which I didn't know before first day, which is very handy because I think then the user still sees the solution and which would be good for pedagogical purposes and for time checking time, I guess. Yeah.
Thank you first. Okay, just a mathematical thing, when you were talking about all these the sets of possible mappings and so on, for the Haskell side, at least it's now, it might be useful to use BDDs to represent those things, so the binary decision diagrams, because all these sort of infrastructure for keeping track of the sets and shrinking them and so on. At least my experience is that's very convenient if you want to work with basically a combinatorial set of things and then question it.
Yeah, I use the strict Haskell sets. I'm not actually sure how they are implemented. Yeah, so for now I kind of just plug different things together.
Because it looks like a logical expression, so a Boolean logic expression, basically.
Yeah.
So that might be useful to you.
Yeah, it's a good point, yeah.
Have you used this to like code call some of the pillars in the Cubical library? Like if you, I don't know. I mean, there's a bunch of terms there that are constructed by hand and that are really hard to read. Like if you dig into like the foundations and it's like, this might as well be magic. But have you like just found a bunch of solutions that are like better or easier to understand or in any sort of regard?
No, so I think this would be the next step. So for now I've just encoded these kind of examples from the Cubical library by hand and kind of saw whether I could retrace these solutions. So this works, and now I think if it's actually usable from Agda, this means we can use it to explore our theories more easily. And that's the last bullet point here. I really hope this could be used for some model proofs as well, because constructing these high-dimensional cubes is not really what we are built for. So yeah, the automatic reasoning capabilities can be used there. I think we can maybe come up with something new.
Yeah, it seems you would also want to like to call Haskell code from within Agda. So maybe yeah, what Phil proposed would also make things a bit simpler. But your goal simply is through a binary, through the XATC, right?
Yeah. Yeah, the parsing that I do is really like this last step is just parsing Agda syntax into an Agda term. This is not really. Like Amelia said, essentially we just need a primitive into a reflection component which takes the string and then runs the internal parser of Agda and then gives this back as a term. So kind of a string to term primitive is kind of
so maybe, I mean, you have control over the output, right? You could produce a already sort of a string that looks like the term data type of Agda reflection, right?
Yeah. So this is what like the Haskell code does.
Okay.
It really produces like some number ij and then some.
But then you don't need to actually parse Agda, right? You only need kind of a parsing instance of this term data type.
Yeah, exactly.
And I mean, so basically, you want something that's like the what is it called? It has the read type class.
Yeah. So
I mean, I have a library for doing type class derivation, and I can derive show. I think read is like, I mean, it's the reverse of show. It should be. I can probably do this in an hour or something.
That would be great. That would be, yeah, I think it's just about connecting some wires. It would be great actually.
Yeah. I mean, so of course there's the problem with mutual recursion, which my thing actually solves, but I haven't tried it with only tried 2 mutual types for now. maybe I run into some issue with that, but it should actually be easy.
Yeah, in this case, it's very simple terms actually, but need to be fast. Except on the H comes something like that.
Okay, good. Thanks again. So we are running already half an hour late of schedule, but then let's